afternoon. We have the pleasure of having Tomas presenting to us on this video about his work in what is done previously and what he's doing. He's a postdoc in physics. He's the past 2 years, and he's going to introduce himself to us and his work. We have a couple of students working on similar topics, so that would be a good forum for discussion. And with that, we'll start.
Well, thank you for the introduction, Rolton. And thank you for everyone for being here. I'm going to go a little bit on this topic of meal delivery. And I'm glad that some of you are working on this because that means I'm going to get at least a couple of questions, I hope. Okay, let's just jump into it. I'm going to start with some of the context, and then I'm going to go over the problem definition. I'm going to tell you an overall picture and some details about how we solve this problem. And finally, there will be some time for some computational results and some managerial kind of insights that people in the business school love. I hope you find them interesting. So meal delivery is essentially a platform. There's like an app. Think about USyd, DoorDash. There are 3 main stakeholders. You have the restaurants, you have the drivers or couriers, and you have the customers. Customers place orders, the restaurants prepare them, and then finally the couriers should take them to their customer location. All right. At any point of time, the platform offers this order to the couriers. And the couriers can either reject or accept that order. Right? So sometimes they accept, sometimes they reject. If they accept, then the platform is going to pay to the couriers an amount that is proportional to the distance that they travel. When they, so that's kind of like a first cost, right? When they deliver the order, then there's going to be some cost of delay. If there is some delay, the platform is going to be hurt, it's going to be damaged by it's going to damage the reputation, right? So there's like some intrinsic cost, or there is some interest there of the company of remaining competitive, right? Couriers can log out, right? They decide their own working schedule, and they can log in at any time. The system continues like this, more orders appear, and then the platform is going to offer the couriers again some new meals that are new orders that are right? Now, what happens if an order gets rejected? For many times, then at some point the customer is going to be pissed off. And then they're going to drop off the order. They're just going to leave the system and they're going to go to another place, right? And then it's going to be another cost. A third cost dimension that depends on also is how it reflects on the platform reputation. Okay, so this is lost order. Okay, so that's kind of like the general setup. What happened here was that in 2024, Meituan, in partnership with the Transportation Science and Logistics Informed Community, released a week of data of Meituan's operation. And the idea was to, have researchers openly participating in this challenge, trying to improve the efficiency of the Meituan operation. Okay, there were over 20 teams from different universities, 9 different countries, and this was the one that won that. What I'm going to do. All right, who's Meituan? It's a monster. It's really, really large, like a very large car. You can imagine that because it's large, it's also hard to move, right? So it's challenging to, for example, deal with 150 million orders in a single day. That's quite a monster, like a logistic nightmare or a dream if you're interested by challenge, right? They have over 14 million active restaurants. It's difficult to make decisions in this kind of setting. Okay, so the question that we're trying to address is the first question that we had was like, well, what are the main challenges that this company has? So let's look at the data. So what's behind? First of all, the demand is heterogeneous all the time, right? You have lunch rush, dinner rush. Typically, the couriers also log in and log out following the demand and the incentives of the platform. So you have some sort of temporal dimension. But it's not only temporal. You work in transportation, you know, this is also a spatial challenge involved. So there is like an spatial heterogeneity of orders and customers and of course couriers, right? You have heterogeneous vehicles. These vehicles have different capacities. They have different speeds. They have different ranges. And what is worst of all, or more, well, not worse, but it's also really bad, is that these couriers are independent contracts. So they decide when they log in, they log out, they decide which orders to accept and which ones to reject. Right? You have the combinatorial challenge. How do you do the routing? So in a sense, how do I set? And how do I assign them to different, right? So those two decisions. And it's like an optimization kind of challenge. And finally, well, not finally, but also like a very important component of this challenge is that decisions today are hard to quantify. The effect of the decisions today are hard to quantify. If I make an assignment to now, at this hour, I may only see the effects of that decision 2 hours later. And how many different paths, like from this, like a stochastic system, can you have in a 2-hour window? Many different possibilities, right? So how do you assess all of these possibilities? All of these like different paths of uncertainty from a single decision, right? So it's that's like the kind of like dynamic programming kind of curse of dimensionality, right? And yeah, curse of uncertainty, right? And finally, now that this is your final challenge, you only have one path of what happened. You only have one sequence of a snapshot of what the platform is and the states of the platform. But you don't have what would have happened if I made a decision. You don't have that information. So what I want you to have from this slide is there are 3 main challenges. First one is the lack of these counterfactuals, the what if kind of what would have happened if I made a different decision. The effect of on the long term of my decisions today, and the combinatorial optimization, how to do the route and the assignment of orders, right? Okay, so I'm gonna go over these challenges. I'm gonna go over first over the challenge of the counterpart. Okay, so for this, you have heterogeneity of the demand over time, and you have it also over space, right? You can see it here. At lunchtime, there are some red spots. At dinner time, the red spots are different. You have like a spatial heterogeneity, right? So what we can do here is actually drop and not have any assumption on the distribution of how orders are. Just go over with the empirical. And why do we think that this is the best way? Because you don't have like any assumption of this, and demand typically follows patterns. People that use meal delivery generally always continues using the platform, and every week, every time at lunch they order overall to the same person, right? You can use the empirical distribution. And for the heterogeneous couriers, the first aspect is you have this active travel time, right? And the service time, like how much time do they spend in the restaurant, or how much time do they spend delivering the package? That you cannot do with an empirical distribution, right? Because you don't have the alternative. Like how much would have taken this courier to travel to this other one? That never happened. So for that, what we do is use a boosting regression tree to predict the travel time plus the service time using a set of algorithms. Things that are actually like the courier ID, what is the origin and destination, what is the time of the day, the ID of the restaurant. We use all of those things with the observed operations of Meituan, and we actually can predict this travel time plus the service with a 2-minute depth. Good enough, right? Let's see, next. We have couriers that decide when to log in and where to log out. All couriers have the same patterns all the time. Like, you wouldn't actually need to predict this too much, right? But they're like quite unpredictable. Sometimes, some of them, this seems to be their main source of income. So they work at a very predictable patterns every day. Some of them, they log in once a week. It's probably like a second job they have. It's only to earn some extra money, right? So again, this is a stable source of income. This kind of distribution shouldn't change too much. Right? People that depend on this income or that don't rely that much on this income are not going to change behavior so much. So again, empirical distribution. Finally, we have the travel times. Sorry, not the travel times, the acceptance or rejection. So if I offer this order to this courier, are they going to accept it? How likely is that they accept it? And for that, again, we cannot use empirical. We never offer that order to the other courier, right? We don't have that information. So again, we use machine learning, we use boosting regression trees, classification trees, and with that, 85% accuracy, life is good, right? Okay, so that's for the counterfactuals. You see, we have like a line calibrated there. Then for the other aspect of the challenge is the how do we make decisions, right? And how do we incorporate the long-term goal? For that, I'm gonna ask you to be a little bit patient. I'm gonna tell you in a second how we address that. Okay, that's gonna be kind of like the main juice of the talk, the nice part with all the math. And I'm just gonna say that for the lack of counterfactuals, we built this simulator, and now this methodology that we propose is gonna use this simulator to learn, to train their folks. Okay. All right. So let me give you a formal setup of the code. Okay, this is the formal definition. We're gonna use something that is called sequential decision process. Okay. For you that haven't, the ones that haven't heard of that, it's this generalization of a Markov decision process. Okay. So this basically is, for us, this is a Markov decision, right? With all of their problems. So what do we have in a Markov decision process? We have a state. What's it going to be the state? Well, where are the couriers? How many orders have each? How many orders are not assigned? Are active but not assigned? What time of the day? What day of the week? All of this information that is like the chess of the state. Where are the pieces in the board of chess? All right. Then we have the policy, which is our main method to solve this problem, right? Something is going to come out with an action, a set of assignments of orders, new routes, right? And that's the decision. From this decision, we plug it into the simulator, and the simulator is going to tell me what happens with courier and what happens with essentially. So which couriers log in, log out, how do they move, which order did they accept or reject, and what happens to the orders, which ones were lost, were delivered, and which ones were assigned. So, all right, and then this loops over this this is the whole process, right? And my main goal here is to obtain a policy that maximizes revenue or minimizes cost. And this cost is discounted. And here I give you the intuition. If you make a decision today, say you make an assignment, I'm gonna ask this person to go deliver this stuff. Will that affect my cost tomorrow? Probably not, right? Like everyone's gonna go to sleep, system resets the next day. So we calibrated this discount so that in the long term, over a day, your decisions are not affecting the revenue on the next 24 hours. Yes. Yes. It's based on this simulator. So we have this boosting classification tree. It's no, it's a simulation. So it's a random draw from this model, from this calibrated. They may reject or accept. I don't know. I'm not observing that at the moment I made the decision. I make the decision, and then the simulator will tell me what's going to be the next step of the system and what is my reward. No, you're assigning it to a single query. And here I need to be more careful with language. An order is not assigned until the courier accepts it. Right? I'm offering the order to a courier. The courier accepts it, then it's assigned. And it's one at a time. 30 seconds. If you go 2 orders at the same time, you're gonna maybe have 2 acceptances. Yeah. And offering bundles could be a little bit like overwhelming for us. So you don't want to offer them 3 orders. Offer them 1. 30 seconds. Yeah, delta is 30 seconds. So it's like discretization of 30 seconds. All right. So we deal with the challenge of the counterfactuals. Now we have 2 challenges remaining. As I said, the combinatorial aspect, how do I make assignments and routing, and the temporal dependence. What is the long-term effect on my cost, my decision, right? So for this is the general picture. The next 3 slides, I'm going to open each of these yellow boxes. I'm going to tell you what they are. But this is how they work together. So first, you have a value function approximation. The value function approximation is it's a function that predicts based on your state and action what is going to be your future goal. Right? So we have a functional form. This value function approximation is used by hyper-heuristic. Hyper-heuristic is just a heuristic that uses heuristic. So it's a heuristic of heuristic, right? So that's pretty much, you can call it a heuristic. And then this hyper-heuristic is used by a reinforcement method that is called SARSA as to train a policy. Okay, so this SARSA needs two things. It needs a functional form, a value, an expression for the value function approximation, and it needs something that gives it a policy to actually be able to find new solutions, to find action, decisions. And these things are going to be working together. This is the training. It looks over this forever. And once you train your model, not forever, right? Once you train your model, you just use this value function approximation. You call it with a hyper-heuristic, and then you get a decision. Yes. Yeah. Pick up, delivery, pick up, delivery. So the decision is also, if I'm going to add a new order, where do I insert them, the current value? Good question. Thank you. So how to assign plus how to route. Yes. Okay. So is this part here, right? You have a stochastic travel time. In practice, the delivery platforms may tell the couriers what route to follow. May tell them, but usually they don't follow the route the platform tells. So in a sense, they all follow their own route. They know the city where they're, right? So that's why it also makes sense to use the machine learning model to predict the travel time.
Where the drivers are.
You know, you track that. You can track that. I mean, the platform would track that. What we do is use the point of the next destination. So you know where he's going to be at a certain. I mean, you predict where he will be at a certain point, but you don't observe that. So this is the training algorithm is oblivious to go to this circle over here of the simulator. Simulator not used by the algorithm to make decisions. It's used for training. Okay. So what I want to say here is you keep track of some sort of proxy for the not the exact location. The platform in practice does have the location of the courier because the courier has the location activated in the phone when they're in the platform. So you should use that. All right. So let's open this value function opportunity. So I want to predict the future cost of my decision, the long-term discounted cost, right? And I have a few things that are actually very easy to come, right? So say we are in a different setting. We are selling newspaper, right? Selling newspaper. I want to predict, my profit based on several decisions. One of the things that I will not have to include in my profit is something that I know or I expect, like have a very good idea of what is going to be the profit of it. So in this case, if you make an assignment, and you tell the courier to go this route, this distance, right? Then you can immediately incorporate that into it. Because you don't need to like incorporate that into the approximation. Just adding more error, more components to the claim. So in a sense, what you want to predict is something that depends on the difference between what I expect to earn and some sort of cost that is very easy to compute. So that's why we have this kind of like immediate cost. And in the next slides, I'm going to talk about this immediate cost. I mean this is zero. All right. And then you have the other component. That is what you're trying to predict. Now, for predicting this component, what we do is look at how many orders are active, how many couriers are active, what are the average distance from pickup to destination of the different orders that are assigned. So we use all of this information, and there are like perhaps nonlinear features multiplied by parameter, linear, like linear function, right? To approximate this value function. You can use anything you like here. At this point, any machine learning model would do, and would be good enough for predicting the future cost. You can use a neural network. But the problem with the neural network is that it's not so interpretable and it's not so scalable. If you're gonna call this like millions of like a million times before making up your mind in less than 30 seconds, calling a million times a neural network, it takes a lot of time. Unless you have like monster servers, you are not gaining that much. And the second thing is this model is very interpretable. So you can actually explain to someone why the platform is making a specific decision. So maybe the main driver of why assignments are done this way is because the distance is the most important thing. They want to maybe minimize the average distance that courier travels, right? So you can learn that from the data. And you can give an interpretation. Yeah. Absolutely. Yeah. That's true. That's true. So for that, we use the shortest path. But this is like okay, you can think about this in the other way, in another way. You can use this is a prediction of the immediate cost. It can be a feature. If you normalize this equation by the weight of that feature, you're essentially just reducing the dimension of the parameter space, but you're getting the same thing. So this is the right part is predicting what is the difference between this prediction of immediate cost and my actual cost. But you're right, it's a prediction. So we're using the shortest path. We're assuming that the speeds are homogeneous for the delays and the lost orders and all of that. But it's very easy to roll over and to see what is this cost. It's very easy to compute. Yeah. Yeah, that's also true. Like, but you still need to predict because you're predicting your decision. What is this additional cost that is gonna have in the future, right? So in a sense, even if you have very accurate information of the position of the couriers that I think that the platform would have and would use, you're still computing a proxy. It's not exactly the real deal, right? The real deal comes, it's the aftermath of the situation. You only observe it after it happens. And that's when you train, you retro fit the system. All right, so how do you train this? We want to train this data and these parameters. How do we train this? And step steps. And it's not a dance from the 19th. Fun, not fun. All right. SARSA, so SARSA stands for state action, reward, state action. Okay. So in a sense, what it does is bootstrapping the value function approximation that is trying to learn in the training of the parameter theta. Okay, so it's going to give two parameter thetas. One copy keeps the best theta, the ones that is most accurate. And another parameter is keeping the theta, actually not the most accurate, the one that maximizes profit, expected profit. Okay, I'm going to keep a theta that maximizes my profit so far, the train theta, theta star, and another theta that is the one that's used for exploration. All right. So how do I going to train this? First of all, is n step. Let's assume n is 1. So what I do is I go one step back. So I'm standing at time t. I'm going to look at my decision yesterday, and I'm going to observe my cost today, right? So I observe some reward. I use my reward plus my value function approximation in my current state to train my approximation, the approximation that I had one period before. Okay, so bear with me. I'm going to go n step back. I'm going to see all of the rewards that I receive in these n periods. I'm going to compute this g, which is an approximation of the value function that uses bootstrap. So it's calling itself to approximate it. I'm going to keep a tuple of that information. I'm going to have take, action, and reward, and value function. I'm going to put that tuple into a mini batch or a memory bank if you want. And then randomly, uniformly from this memory bank, I'm going to sample one tuple and I'm going to use it for training. I'm going to do one step gradient. Okay. Why do I sample randomly? I don't want my decisions every n periods to be correlated. Right? So this step is necessary actually to reduce the variance of the training of this thing and to reduce the bias. Then I'm gonna do one Monte Carlo simulation. So you can think of a day. I'm gonna simulate a day of operations using theta and using theta star. And I'm just gonna keep the best. The best of the two is gonna be stored in theta star. I'm gonna do this many times, and I'm gonna step out when I'm ready. I have a theta star, then I'm happy because I try enough, right? So this is n step subs. I didn't tell you how I computed the policy, right? How I computed the decision. Decision is here. So this is going to be given by the hyper-heuristic. This is the hyper-heuristic. As I said, it's a heuristic of heuristic. What kind of heuristics? The ones that are relevant for you, right? It really matters depending on the application. For our application, a sensible heuristic is let's destroy the solution and reassemble it by some measure of efficiency. Say, tighter delivery times or fewer distance, right? So I'm gonna try with all of these heuristics. And this hyper-heuristic uses model based on Markov chain to get the best, the heuristics that are better to implement. Okay, so I'm gonna have one state for each heuristic. I'm gonna have another state for each heuristic that signals termination. And what I want to learn is the best transition probabilities in this Markov to maximize problem. Again, maximize. All right. So, for example, this is one run of the hyper-heuristic. I'm going to start with a random heuristic. This can be based on these transition probabilities. I sample it random. It's hammer. Let's destroy the solution. Then, with probability of the transition to termination state, I'm going to either terminate or I'm going to go to another heuristic based on this transition probability, right? Okay, I randomly sample, I get another heuristic. Okay, repair the solution. Make an assignment based on delivery, whatever, right? Then again, improve the solution in this other way. Maybe split it and swap one. And if I finish, I implement this sequence of heuristics. So the hyper-heuristic is learning the best sequences of heuristics. And I apply excellence to my current decision. I can initialize X in any kind of, for example, like do not, right? I evaluate this new solution based on the value function approximation, whatever you want, or a Monte Carlo. And value function approximation is probably more efficient. And if it improves cost, I'm going to keep this new solution, and I'm going to update the transition problem. So I'm going to do this for a while before actually executing the solution. But after I'm done, my transition probabilities are trained. So I'm not going to start from scratch. Next time I call this hyper-heuristic, it's already trained from the last time that I call it. So it keeps on training online. Okay? And this is how it moves. So that's the whole setup. Okay? The whole function of it. And we wanted to test this against like several benchmarks. The most stupid here. The most straightforward is to just look at all possible assignments of orders to different couriers. So I look at all of the pairs of couriers and orders that I have, and I'll assign it to the one who's that have the lowest insertion at the end of the row. So it's like, you know, if I get assigned a route, I'm gonna go. I know that it's gonna go to the end. So if I get assigned an order, I know that it's gonna go to the end of it. Yeah. Essentially, yes. So you have a current solution. You apply this sequence of heuristics that locally change the solution. You assess it if it's better. If it's better, you keep it and you update the transition problem. And now your new solution goes back into it. So you keep it running for some time until you have run out of seconds. It's like a linear, but you may work with several intelligence. Yes. So the heuristics are fixed. The transition probabilities are changed from each time you call it. So the next time you call it, you already have string transition problem. You're not going to start from a, you know, system initialized from scratch. Yes. Bro. P0 plus the sum over the feature times the parameter. So you're right. I'm not being very clear here about what is the function that I'm mapping. So you can use whatever. So if you have a different problem, you can use this. How do I assess it? Actually, I tried two alternatives. I tried two different alternatives. First, I use the hyper-heuristic with the immediate cost. And in another setup, I use the hyper-heuristic with the value function approximation. You can try both. That's pretty flexible. If you start with a transition from definitely a plateau. I give you a fixed amount of heuristic. I'm not changing the heuristic. What I'm changing is how I sequence and with what probability certain sequences appear. All of the above. Getting better because you're training the parameter. Getting better because you're training the value function. Right? So you are learning the man pattern. You know, the value function approximation knows at what time of day you are standing. They know that a piece of the man is coming in the house. So these things are actually working or working in conjunction. They improve conjoining. Very possible. Not saying not very good. We only have one Meituan data. So the simulator was also trained to the extent of the distribution that you can get from this data. If you give it like years, weeks and weeks of data, yeah, it might. I be honest, I'm not sure. That's a philosophical question for me to answer. It's interesting. I don't know how. For me. Okay. All right. All right. Simple policy observes immediate cost, but it does the best insertion. So it tries all the possible combinations of where to insert orders, which courier to assign it, offer it, and yeah, that's pretty much it. And then the end-step SARSA policy that uses the same action space as a simple policy. So all of the combinations of possible insertions and offerings of orders to every single courier. And that one, the only difference is that instead of using the immediate cost, uses the immediate cost plus the value function of each. This is the setup. This is the set of things that we fix. And here are the results. So lower is better, right? Relative cost change, the lower the cost, the better. The red line is the mean. You can see the fastest policy performs pretty bad. I mean, every order is inserted at the end, so it's pretty limited. Then the simple policy still performs worse than the other one. And the difference between them is actually about 10, 11, and 12%. So each of them is like improving cost like a 1%. Now remember, this is a company that gets revenue for 600 billion a year. 1% of 600 billion is still a lot of money. All right. So still you're gaining some serious amount of money from right by going more complex. Then if you observe here, lower bottom, there is actually not much difference between different methods. Why? I mean, you have a boring day with a few orders appearing and a lot of couriers around. Well, it doesn't really matter what, right? You're gonna pay small amount of because of distance, but you're not gonna get late. You're not gonna lose orders. There's no much cost difference on days that are good. Now, on days that are bad, the difference can be significant because the system gets congested, and your decisions, if they're bad, they impact you throughout the whole day, right? So it kind of like it's an effect that increases with how busy the day is. So we look at this. We look at an average day. We look at the high cost day, and that's exactly what is happening. In an average day, you get the dinner, the lunch rush, and then the system sorts of recovers. It observes high delays right after lunch, right? Because people are getting their orders late. But then kind of like recovers, and then at the end you may have some of those orders because there are not enough couriers. But no, it's not such a bad. In a bad day, you have very little couriers, very few couriers, and after the lunch rush, system cannot recover, stays congested, and it's just losing orders, right? So this is where these machine learning methods are actually improving the system. So, well, it looks like by increasing the number of couriers, we should also get like better results, right? And we actually did get way better results. By just increasing in 10% the number of couriers that connect to a platform, we get half of it. Which was very surprising. I mean, the system seems to be congested by looking at the data. And if we duplicate the amount of couriers, then we don't observe that much marginal gains. So that's why at some point, having too many couriers is actually not helpful. All right. So that's pretty much it. So our main contribution is this unified framework, combining the value function approximation. I mean, the simulator, the reinforcement learning, and the hyper-heuristic work, right? A lot of work that we did here was feature selection engineering. So that was something that we don't show too much, but it's actually finding these features that were relevant for all of these machine learning models was a pain. And these methods are very strict. So we actually, the SARSA policy, the simple SARSA policy, gets the solutions in half a second. The hyper-heuristic gets it in 27 seconds. So definitely implementable. And this approach has the advantage that it's very transparent. So it can be interpreted. After you calibrate these models, you can look at these weights and you can actually understand what's going on behind. So it's not like it's going to say, oh, yeah, you know, it's because the machine learning model says. You need to do this, and I did machine learning model says. Right? And people don't trust that. So sorry if I went a little bit over time. I hope I love to take any more questions.
So we have a question one on Zoom from Andres. I'm gonna read it out loud. Is there any component in predicting the likelihood that the rider accepts, and that the rider can decline an offer or accept it? Where did you discuss about that component?
So this is part of the simulator, right? So I briefly discussed this, not too much detail, right here.
So I think the question is not about the simulator, but where in the SARSA modeling, the whole framework that you find the action, you consider that behavior of the couriers.
So that's in the features that we select here. So, so the system workload has different components. Has how many orders are active, how many are assigned, and it has how many orders are on hand per courier, and how much time have they been working on the platform. If you know how much time the person has been working on and all of those things, the system eventually learns that that's an important feature. It's important to consider before offering someone that this person has been, has like this 4 orders on hand, or that it has been working for 3 hours. So it's unlikely that it's going to accept it, and that reflects on that being a poor decision, that assignment. So yeah, this red box, the large red box here actually hides a lot of features. We consider 14 different features, but I cannot go into detail because they are a bit complicated. Some of them are Fourier series that capture demand patterns. So yeah, you can also read the paper if you want, and scan that QR code and read the paper. But yeah, I thank you for the question. I hope I answered that.
That's Andrew's question. Yeah. Any other question? Yes, there's one.
But so the heuristics is not random, right? But yeah, this is all based on literature that is called Meituan bandit literature. So for training this algorithm that I showed you for training the hyper-heuristic, it's based on X3. That's exploration, exponential. And it's an adversarial approach. So it's assuming kind of like the worst case distribution. So to deal with that, they are random. So it won't get stuck every time on the same local minimum. It will get stuck on a local minimum, yes, because these are heuristics and the problem is highly non-complex. It's finding a needle in a haystack. It's quite difficult to guarantee any kind of optimality. But yeah, this algorithm guarantees essentially that at some point you're going to visit the open. Yeah. Thanks for
Any other last question from visitors? No? Yes.
Whether really information from that's and more than understand.
Right.
So how can you present what the position correct that powers of the data in the early power? On possibly paying more for you that you're not present in the well, yeah.
So, yeah, thank you for the question. I think that's another thing. Because it's a very, so it's, I think it's, has a lot of intuition of why things, how things can be managed in a better way. So, yeah, if it's raining, you know that. You may have incorporated that into the model. I did not incorporate it. I didn't go to the weather station and check if it was raining someday. But you can incorporate that as a part of the state. So it's definitely actionable because you can see in the model that that weight is high. Then if you want to prevent that sort of situation, there is another aspect that I did not consider. And that's because it didn't come with it from the data, and it's the price. How much do I offer to the courier for delivering this thing, right? That we did not do, we don't observe. And if you have that information, that for sure will go into the value function of optimization for a start. And you can also, based on historical data, you can do a regression classification tree, or you can do a logistic regression and try to interpret like what is that kind of a DC, that how much supply you will get by increasing $1 fee. So yeah, those are very interesting questions.
Good. We'll thank him again.